I'm going to talk about maximizing small diameter inductive tube welding system performance. This is a project that we've been working on at Fluxtrol for some years, but really focusing it on over the past 5 to 6 years. We'll give a little bit of overview. I know not all will be familiar with the induction tube welding process. We'll cover a little bit of what it is. Then we'll cover what is this component called an impeder, and what are the benefits of it in a tube welding system, and what type of materials do we have to choose from for these materials. We'll cover some case studies for tube welding systems where you can see these major improvements to the system. And then we'll cover about how we're working to offline perform both virtual and physical validation of these soft magnetic composite impeder designs to prove them out before we take them in a plant. Then we'll circle back and summarize the findings. Induction tube welding is not a new process. It's been around for over 60 years, and it makes a variety of different types of tubing, both steel, aluminum, copper, but a lot of it is steel tubing. The first patents on the process were from the 1940s, and the first known industrial high-frequency inductive welding applications were in the 1950s, it appears. But the induction tube welding process involves, you start out with a coil of steel. Okay, that coil of steel is then uncoiled and goes through a series of rollers. So these rolls, their role is to form into a tubular structure. Then it will pass through the induction coil. And after the induction coil, you get the final pressing where we'll close the profile of the tube. Then it's typical afterwards you'll have the external bead cut off, but many times there's a lot of other processes downstream from that. This is from a recent paper by the Technical University of Chemnitz, but shows the layout of the active line that we're looking at. Here is an actual close-up of an induction tube welding process. Here you have the incoming steel tube. It's passing through a very small induction coil. You have your squeeze rollers, and coming out you see that the weld seam is quite hot. So the rest of the tube is cold. So it really focuses the energy right on the weld seam where you need to make this joining process. The other thing is there's lots of water everywhere, and this is like a vent for steam removal. It's a very complicated process, but it's really a simple installation. If we look a little more into what's happening in that, our folks say that's the heating and joining process. The induction coil is wrapped around the open profile. Normally induction heating, you have a closed profile, and the currents will just flow right around the closed profile in opposite direction of the coil. When you have an open profile like a tube, the currents, they flow around, but then they hit this edge, and they can't go over here. They have a choice. They can either go this way towards the welded bead joint, or they can run back along the tube and eventually return to the other side. Or they have a third option, which would be flowing along the inside diameter of the tube. And some of them go each way. Now, how much go each way depends on the geometry and the layout of the system. The inductive tube welding market has been evolving over the past 20, 30 years. There's been big progress in that area in the transition from tube generators to solid state generators. So this basically pushed tube generators run at about 50% electrical efficiency, and we're talking about the power supply circuit, getting the power to the coil. Meanwhile, the solid state generators run at over 90% efficiency. So that's been a major reduction in the cost of induction tube welding, is by upgrading and modernizing this equipment. So along with just the basic efficiency of solid state versus a transistor tube, you also have the availability of higher, more efficient power at a choice of frequencies. Tube generators, they worked at 450 kilohertz was a common tube, but you only get certain set fixed choices of frequency. With solid state, you can generate any frequency that you want. So we've also got improvements in material handling, process monitoring and control, material cutting. A lot of these tubes, after they're processed, are then cut to length. And all of these things create the potential for higher line speeds, more productivity, reduced cost to produce a tube. So there's been a lot of investments in there. And now that we've upgraded all of these things, we're starting to find then more and more of these tubes for small tube installations. The limiting factor is the cheapest part of the whole assembly, which is the impeder. What is an impeder? An impeder is assembly that contains a soft magnetic material that impedes or prevents or reduces or makes it harder for the current to flow on the inside of the pipe. They're typically manufactured using ferrite materials, and they're fixtured within the forming tubes. Here's some different sites that ENRX is one of the major players in the welding consumable. I took this picture from their website, but there's different types of configuration, water flowing one way and returning, water flowing through, different mechanical connections, but the ferrite sits inside generally a casing, and sometimes there's other things that go in there as well. Let's look at a case study that we presented about 5 years ago that really started to increase interest in the opportunity to improve the impeders. So this is done at an industrial tube mill. It was a short test, it only ran for 20 minutes intentionally. But in this mill, they're currently using a ferrite impeder, which is viewed as state-of-the-art. We did the identical geometry with the Fluxtrol 75 material. Okay, the line was run for 20 minutes at the same line speed, same setup. The only thing that we did was replace one feeder with the other, and then the operator adjusts the process so that they get a good quality welded tube. It's an apples to apples comparison, and here you can see this line running. This is the incoming tube and those rolls we talked about. Here's the induction coil. This one's set back a little farther than the rollers and run a little hotter than the other. But here's the heat before the weld seam, and here's the heat after. Let's see if I can get this to back up. And afterwards, you can see that external bead is cut right off there, and the tube goes down the line. In this case, we had a 19 millimeter OD tube with a 3 millimeter wall thickness. That's a pretty heavy wall thickness for this size of tube. And the weld V angle was about 2 degrees. The inductor here just shown conceptually was a single turn inductor. In reality, I believe it was a 3-turn inductor. The coil dimensions are here, and it was set back a little bit farther from the apex than is typical, about 64 millimeters. And because as you start to add up the wall and the casing and the tolerances, that doesn't really leave that much space for the magnetic core. And the magnetic core was about 230 millimeters long. These were values that we got off the generator when we multiply the inverter current by the transformer ratio. It was an ENRX welder and it's series power supply, so it's a pretty accurate calculation. So in production with the ferrite heater, it required about 7,300 ampere turns, and the generator was consuming 325 kilowatts for 82 meters per minute line speed. Okay. When we replace that and went the same speed with the Fluxtrol 75, only 5,000 ampere turns were required and 200 kilowatts of process power. So once we got to here, they really weren't able to turn it up any farther without, at a certain point, what they found is if you just keep down up with the ferrite impeders, eventually you keep turning the dial, but not much more happens. We'll explain why that is here in the next couple of slides. But when we used the Fluxtrol 75, they were able to turn it up and increase the speed 20% with only a 10% cost in power. At that, we had over 30% lower current and 40% lower power for the same production speed. And you can see a link to the paper where this was published in the chat, I believe. They'll be posting the different website links so that you'll be able to click on them and go if you want to find more information later or copy and paste them. So now we start to open up the kimono and see what's going on inside of the tube here and with the magnetic flux concentrators in this. If we look below, Fluxtrol 75 has a saturation flux density of 1.4 Tesla. Meanwhile, ferrites typically have a saturation flux density of between 0.4 and 0.5 Tesla. What saturation means is that once you achieve saturation, the basically additional magnetization kind of takes the same cost as air. The material behaves like air above that. It behaves very well up to that level, much more favorable path, but beyond that path, essentially the slope is parallel to what would be if there was no concentrator in there. And you can see that with the Fluxtrol 75, really there's a concentrated zone of flux under kind of the back third of the coil, and then that falls off in both directions. Meanwhile, with the ferrite, you see a much wider distribution of higher flux density. But the maximum value isn't as high just because essentially the magnetic material stops working at this point. Now when we start to look at the current flow, so we can see where all that extra current went. So that extra 50% of current, it's distributed along the inside of the tube, right? Because the tube wall thickness is only 3 millimeters, but the width of this tube is much larger, the resistance isn't high of the tube. It's not huge levels of loss in the tube, but it is where all that current goes. And all of the supplying circuitry, the coil, the heat station, the power supply, all of that, the losses in that are proportional to the current squared. So this really, where we've gotten all our efficiency savings, is preventing this. That's really what the impeder is supposed to do, is stop this. We just got to a condition when they kept turning up where we went back past what the impeder was capable of stopping with these ferrites. Meanwhile, at the Fluxtrol 75, you don't see this current, or at least it's quite small. We're keeping the heat on the weld seams. So that's how we achieve these very large shavings in this installation. So if we say, what does this mean? A lot of people are being challenged with reducing their carbon usage and lowering their carbon footprint. When we turn this up, we could use 100 kilowatts lower power and move at 20% higher line speed. This was not a limit of our material. The only reason we didn't go faster is it used to be the induction system was a bottleneck. Once we replaced it with this material, we hit a new bottleneck. The next bottleneck we hit at 96 meters per minute was the speed of the flying saw. So they couldn't cut the product any faster. So that wasn't why do we stop here? You're getting 20% more production for 10% more power. Why not keep going? The line couldn't go any faster. We removed a bottleneck. That led to 45% lower kilowatt hours per ton of tubing produced. That means for the same amount of material processed, it took 45% less energy to produce that amount of tube. With these type of powers, and this is a middle-sized tube welder, some are bigger, some are smaller, that leads to a reduction of 437 tons of CO2 annually. If we assume 2 shifts, 7 days a week, about 5,000 hours a year of production, that we know that typically these lines will not run that single product, but the assumption is, okay, across the family of products, you'll replace all these impeders and you'll get similar savings. At the higher speed, it's about 480 tons of CO2 reduced over the course of a year. And your energy savings in the US would be about $55,000. That is assuming 8 cents per kilowatt hour. Okay. If you're looking at Europe right now, you're looking at 20 to 40 cents per kilowatt hour. So that number becomes like $125,000 to $250,000 a year in energy savings. Then probably most importantly, if you turn it up, it would take you 730 less hours to produce. Generally, I've heard the value of running these systems is in the tens of dollars per minute. So you start to extrapolate that out, and you're talking about potentially $500,000 of extra productivity. So those are starting to be where you see the real large numbers if they could sell more product. The way I'm thinking of it, and this is the only electrical diagram out there for those mechanical or materials inclined, but if we think about it, the induction coil is the primary of the transformer, and your tube is essentially the secondary. And we have three competing paths for the current to flow in parallel. One is the weld V before preheating, and the other is the weld V after. Now, these are the currents we want. These are the useful heat in the system. The other competing current is that part ID current. And the inductance of the circuit is much larger than the resistance. So how big this inductance is approximately directly proportional to the product of the magnetic permeability of the core and the cross-sectional area of the core. The more core we can put in there, and the higher the permeability. And the bigger that number is, less flows here, more flows over here. The candidate materials for soft magnetic, with magnetic properties for soft magnetic materials, they're candidates used as magnetic cores. We have manganese, ferrite, zincs, manganese, zinc, ferrites. These are the most typically used, and you can see very high relative permeabilities. Now, these materials, for other reasons, really aren't good candidates. People have tried them. They don't hold up. So why are we proposing to go over here to these soft magnetic materials? Because we told them, okay, the permeability is key. Higher is better, right? That makes the core seem much bigger, and these permeabilities are 10 to 100 times larger over here. The thing is, that's over here, right? What happens if we want to go to right here? Okay, this bubble doesn't contain that because there really aren't materials for that, right? And that's when we get what's called saturation. So we'll look at a same size core. I used Fluxtrol A as an example material here versus ferrite core. If you look, here's those permeabilities we talked about. So you have your initial permeability, and then it goes to a maximum and over. And the Fluxtrol stays around 100 as it goes across the spectrum. Now, the ferrite kind of goes up a little bit too, and it's way higher than the Fluxtrol in order of magnitude. But then it actually starts to do what's called the saturation, and then it just falls off a cliff. We can just draw this line where these two curves intersect. And you can say over here, ferrites are better, and over here, the SMC would be better. Another way to look at it is what I call the core magnetic size ratio. This is a metric we're making. And you could look at that value being 1, and that's the product of magnetic permeability and area of the core. Why this is critical is down the line, because we have all this capacity over here, it does create opportunities for us to use different shapes or sizes of cores compared to what is in the ferrite for other reasons and to improve a system. When you see this ratio where over here, ferrites are 20 to 50 times better, as we go over here, the soft magnetic composite Fluxtrol material is 20 to 50 times better over here. If we're not operating in saturation, then the impeders we're using are great, but once we try and cross this threshold, that's where the outperformance really becomes. And the other key factor is it's a relative value. So even if you look down here where the ferrites are still great, Fluxtrol is still 100 times better than air. But if you go out here, now the ferrite's only about 2 times better than air. Meanwhile, the Fluxtrol remains 100 times better than air. We can look at what this means. If we look at, here was a recent case we did with the return flow impeder. So we'll just focus only on the calculations that we made on the impeder core itself. So we removed the tube from the model, and we did leave the impeder component. So inside the ID of the impeder core, there's a brass tube. Passing through the center of this brass tube is a steel rod, and that's used for different processing purposes for that specific tube. What happens is you have these other parts, it leaves very little space available for the impeder core. It really shrinks the area that you could stuff full of magnetic material. The main failure mode of the impeder core was mechanical. We looked at two different SMC cores. One would be, okay, this fits in the same size casing as the current ferrite impeders. And the other one was it fits in a 1 millimeter smaller casing. If our issue is mainly contact with the moving tube that's causing the destruction, if we can make this perform just as well with a smaller core and smaller impeder, then we're less likely to run the tube and the impeder is likely to run much longer. When we do that, now we can start to see how those curves translate towards process parameters. And if you look here, down here you can see the SMC impeders. They do take more, there was two different ferrite designs that they were comparing as well. They do take more current than the ferrites, about 1.5, 2 times. Now that, again, the tube is pulled out of there. In reality, this level will be much smaller. But then you start to see as we hit that wall. And if you look up here, if we wanted to go, for instance, from 0.4 to 0.6 Tesla, it takes about 20 times more current for the ferrite to drive that same level of magnetization. Again, this does not consider the tube. That real level will be lower, but that's where you're seeing your 50, 100% increases in current. We have to keep in mind that these losses in induction coil and power supply and circuitry, they're proportional to the current coil current squared, right? So when you start having to have all this extra current, your overall process efficiency drops pretty fast on your machine. It's not just the extra losses in the tube, but it's also the extra losses in the machine. And you run to either a danger of either hitting a power supply limit or coils start blowing up pretty quick just because they can't remove the heat from the current that they have to carry in order to successfully weld that tube at that rate. And that all happens once that saturation hits the core. So what we're defining now is there's a region where you really have high process efficiency in a tube mill. And that is where you're below the magnetic permeability, and the majority of that magnetic load is in the impeder. The size of that is really potentially the saturation flux density of the core times the area. So we still haven't found a line that could actually run at the saturation flux densities we have. So right now we're validating off of saying if these can run at 0.8 Tesla as compared to 0.4, that's 2 times, you square that, you'll have 4 times the regime of high process efficiency. We still haven't found one that can actually go at that rate, but that's what we're designing all our heater cores for. The advantages of an SMC are really that higher saturation flux density and that time temperature stability of magnetic properties. There is some instabilities in production. Ferrites are sensitive to temperature and stresses, and you do see some oscillations which cause things like micro explosions. These tend to be much more stable, the cores. The disadvantages, cost. They are more expensive. Lower permeability at low fields. Higher losses than ferrites. We haven't talked much about this, but it does require better cooling. And I wouldn't advise these to be tried in a gas-cooled system. And there may be more intensive failure in cases of insufficient cooling, depending on the system. The main opportunities we're targeting right now are small diameter. That means you've generally got smaller space for available space for core, or really heavy walled steel tubes, because actually the amount of current that you need is essentially proportional to the thickness of the tube wall. For small tube applications where the welder is a bottleneck and impeder is in saturation, you can tell that by really, you're turning up the dial, but the speed isn't going up as much as you turn it up. Applications where ferrite and impeder frequently fail due to mechanical impact with the line. They've had to stuff as much core to get good productivity out of it. However, they're so close, any instability and you get an impact and you lose the impeder. Or applications with metallic components inside the impeder that also won't allow you to run past saturation, because once you do, then the loss in those internal components grow really fast. And any application with very short impeder life tends to seem to be a candidate. Here's an industrial case study. This is in the public domain. This is published by others, not by us. This is a mill in Serbia. And there was a 400 to 500 kilohertz power supply with 250 kilowatts power. They tested on a couple different tubing sizes, a little bit more, a little bit less than an inch, OD, 2.5 millimeter wall thickness, or about 100 thousandths. And they were using 13 millimeter OD impeders. So they tested both the ferrite and Fluxtrol A, and they found that they really tested in this study both 10 and 60 meters per minute. This group has published quite a few other studies too, but they found that the energy savings for the same line speeds were between 30 and 50% when using the Fluxtrol A as compared to the ferrite, and that's TDK ferrite, and even more savings if they compared to some of the lower quality ferrites. The Fluxtrol impeders were reported to last approximately 5 times longer in production, which is huge because when a line goes down and it generates one, significant amount of scrap, and two, it takes maybe 30 minutes to change that impeder out and get the line back going again. As we talked about, at tens of dollars per minute of production, you've got thousands of dollars in savings and costs, not even including some of the other benefits of that impeder switch, and those really start to compound over time. In this case, if we look at the higher case, 100 kilowatt hours, we're saving 350 tons of carbon dioxide emissions annually. We did this again with US electricity rates. We're given this in kind of US times, but we're looking at $40,000 annually in energy savings, which is a small number compared to the other savings, but I don't have definitive numbers on those. If that were 20 cents, you're looking at 100,000. If it's 40 cents, you're looking at $200,000 annually in savings, just from energy alone. And that doesn't include any types of carbon taxes or other things that you could use to offset. That's just straight what you're paying from the utility. This was some recent trials from Princeton Company. It's in Germany, steel roll case study. This was done by a group led by Technical University of Chemnitz. And this was about 400 kilohertz line, a small power supply, 50 to 150 kilowatts. This was a smaller tube, a 15 millimeter OD, a 1.2 millimeter wall. And in this case, they used Fluxtrol 50. They used a 9 millimeter ferrite impeder, but they decided to reduce the size of the impeder with Fluxtrol 50 to take advantage of that saturation and give a larger mechanical tolerance to 8.5 millimeters. Even though they used a smaller impeder, they still saw a 40% reduction in energy savings. This was, again, about 80 meters a minute. That's a pretty common speed for these types of mills. The energy savings for the same line speed was 40%. They reported greater than 20 hours of impeder life with little to no sign of wear, compared to 4 hours typical for the ferrite. That kind of 5 times ratio of lifetime. And the smaller tube has less space for impeder, which makes it more prone to saturation mechanical damage. Even though it was a small tube, you're still looking at 87 tons of CO2 per year. Again, this is also US CO2. In Europe, they actually use more CO2 per kilowatt hour than we do in the US because most of our electricity is natural gas. In Europe, they still use a lot of coal. And that tons of CO2 will vary by country. So that's US CO2. And you're getting $10,000 in the US, which would be $25,000 in Europe, which would be $50,000, $25,000 to $50,000, depending on European electricity rates and country. Those numbers are quite large, especially, and they don't even consider any carbon taxes which are coming. These have the opportunity to do some offsets for you. This one was done in the US in collaboration with the Kent Corporation. They're a tube welding, induction tube welding OEM. So they sell systems, aftermarket components. This case, it was 400 kilohertz, 300 kilowatt power supply. This was a half-inch OD steel tube with 1.25 millimeter wall thickness, and 8.5 to 9 millimeter OD impeders were used. This one, I took a picture of the cut part showing you the virgin material, the heat affected zone, and Here is the weld seam. The external bead's been removed. This is showing the internal bead. In this case, we only had energy savings for the same line speed was about 20%. And it passed all metallurgical and structural tests. You say, it's smaller, why did we only achieve those benefits? The human factor was at play. The impeder in this case was only at the edge of saturation for the ferrite, and we used a smaller core, right? So we put less area in there. Yeah, you didn't get quite as much. We did turn it up, where if you start to turn it up, you got into that low efficiency zone if you use the ferrite, but ours you could easily turn up. So we turned it up to 93 meters a minute, and then that was really as fast as the operators could keep up. So if you think about it, this case, I think we're making somewhere around approximately like a 10-foot long tube. We're running 300 foot a minute, the tube's 10 foot. So every 2 seconds, the tube's being cut. And the operators just couldn't keep up with the unloading. So that's the only reason we couldn't go faster. If they were making a longer tube, we would have turned it up quite a bit more and really seen much bigger savings. But even in this case, you're looking at 50 tons of CO2 reduction, $5,700 a year in energy savings, and you're also going at approximately 15% higher speed. So the net effect at the higher rate was in the upper 20s of percents of energy savings per ton of steel. And maybe the biggest thing that was surprising for them is the operators are used to constantly have to fiddle with this line. And they didn't have to touch the settings for over 12 hours of production before we switched to another tubing size. And extremely rare that they would be able to run that long. Typical life, 1-2 hours. Occasionally they'll get a flyer that runs longer, but this was really a huge potential savings for the group. Everything is great, so why aren't these out there everywhere right now? Why am I just hearing about them or doing a webinar? There's barriers to adoption. One, tests on a tube mill are very expensive. These things run at 150 to 1,000 foot a minute. So getting substantial time on a line, there's a lot of product being produced, a lot of values. It is very costly. Validation of a new process can be very expensive depending on what that tube is used for. If it's electrical conduit, it's one thing, but if it's maybe a safety critical automotive structural tube, it's a whole other thing, or an aerospace tube. So ferrite's a proven technology and the current industry standard for decades. This is what they know. SMC cores are 10 to 50 times more expensive to purchase on an individual unit basis. Now, seems like a lot, but keep in mind the normal ferrite might be like $3 to $10. They are really cheap. So the payback is typically in minutes. If you look at the productivity improvements, if you're a production bottleneck, if you look at only the energy savings alone, it's typically several hours in the US, a couple hours in Europe. Maybe the real concern is the SMC losses are higher. So good cooling is required. So we really have to pay attention to our impeder design and our cooling circuit design. That's really been the issue. If we've had a problem, it's related to just the core design, and we have to consider the cooling when we do that. We've developed a method internally where we look at simulation of the welding process, which we showed above, and what's going on over here. And then we've added to it that ability to test and validate outside of the lab with really modeling the loading of the core and then actually testing the loading of the core in the lab and design the cross section so that we can remove the heat. And then the last portion is, of course, actual real field validation with industrial academic partners of our designs once we validate it in the lab. So cooling calculations, we look at two different things. One is the overall flow. Does the overall fluid overheat? Or two, do we have a local temperature issue where we have that high magnetic loading? Let's look back to that model we showed earlier, and we've got our area high magnetic loading, and it falls off. So what we see is mainly we have an axial gradient in flux, but there isn't really a radial. So because of that, we can do a simple electroact model with just a coil with no tube in place. Otherwise, you have all the problems with cooling the tube. So we're focused really in, okay, can this impeder survive in the conditions it's going to experience in the field? And this does a good job of simulating the approximate distribution you would have in a tube mill, and verify that we can do this local cooling and also the global cooling, making sure we have the right overall water circuit, and we also have the appropriate cross-sectional design so that we can extract the heat. Here's a couple pictures of the test installation. We've actually got 3 of these installations now: 40 kilowatt, a 25 kilowatt, and a 3 kilowatt for testing different sizes of impeders over the range we're looking at, and different coil turns to ensure we can match across and test across the whole range of product that we're looking at. In here, if we focus in on the coil, we now have a holder that keeps the impeders centered, and we're measuring the voltage on the outputs, and we're also measuring the current that's flowing through the inductor. We're measuring the temperature in and out right before the impeder, and we're also measuring the flow to the impeder, so we can make good calorimetric measurements. Finally, we're also doing thermal imaging, looking at the outside the casing. We've done this both with transparent casings, and also we're doing it now with opaque casings, which are typical, because we found that sometimes now the limit we're hitting is actually the temperature the impeder casing can withstand as opposed to the impeder. That's another thing that we're looking at and including in our considerations in our simulation. Here is early trial that we did where we're really focused on, okay, how are our models correlating to our experiments? We had the theory, like we said, as long as you have the same cross-section, you have the same performance. We produced 5 different impeders, all of the same material. It was all Fluxtrol A. 2 of those were a typical fluted, radial fluid design like ferrites are used. And then 3 of them were a machined geometry that we made called faceted with flat faces with differential thicknesses that had the same overall cross-sectional area. And you can see that all 3 of these at multiple different levels, these dots represent the different data points. They all tested pretty much indistinguishable from one another, and they also agreed extremely well with our FEA predictions of what they should be. We feel pretty good that we've got a good handle on our test system. The other thing we looked at is, okay, now let's look at our calorimetric values. This was our FEA predictions of what our power loss should be in the core, and these are our data points where we actually measured them calorimetrically and compared them. And if we look at the highest test points up near 1.2 Tesla, keep in mind that's 3 times the saturation flux density of a typical ferrite at welding conditions. We had excellent error in the system, actually better than we really expected. We were really happy with this. You can see it's a little bit more down here, but we know our loss functions aren't perfect, but they're doing a good job of predicting this. Here is another test that we did more recently, and this kind of includes all the bells and the whistles, tracking versus time, and with the closed loop chiller on there. You see our outlets and our inlet temperatures. This was 310 kilohertz, around 0.8 Tesla for the majority. But this one we're really, okay, how long will these survive in a field? So we're doing 4 to 6 hour trials now to verify they'll perform at this kind of standard that's approximately double the saturation flux density, 4 times the effective area of ferrite. If you see, there's a couple early startup points down here, but then we really got into the heavy duty trials and essentially ran it for 5.5 hours successfully. If we look at our comparison of our tests and experiments here, so here's our 3 data points that we ran. In the early points, just enough to get to steady state where they're flowing parallel, and then ran the high level, and those loss values looked very good. Here's our FEA of the internal temperature distribution. Here's our thermal imaging saying, yeah, the casing's getting kind of warm, but it's not failing. This was a successful trial. And the more concern is the local temperatures as opposed to the delta T in the water in this impeder. Originally, we were doing theoreticals, but we found that no one's lines are set up to run over here because this is the current state of the art. Really, what we're doing now, and these are just different trials of different impeder sizes, geometries, test conditions we run for different durations. But now we're standardizing all this to saying, okay, we think if we can run here, we can fit the market's needs. Because you remember we talked about that cross-sectional area and permeability. I can make any of these to survive at saturation, but the way to do it is remove cross-sectional area. I'm trying to not remove cross-sectional area. We're trying to keep this area approximately the same as this. We'll open up that productivity band by 4 times. And we think that's more than enough for the existing market needs at this time. And so we're starting to consolidate a lot more data points right here, which really create a lot of opportunities in mills and verifying that they can last 4 to 6 hours. When these ferrites are really heavily loaded in these challenging applications, we generally find that the lifetime is in a couple hours. So this will be already a lot more than that, and we don't think people can really get to here in the majority of applications. Just to close, many small tube welding installations are limited by the impeder. SMCs have the potential to greatly improve the performance of these installations. We're getting pretty consistent numbers of 20 to 50% energy savings / carbon reduction. This is a big one that we're seeing a lot longer lives in those instances. A lot of it's through shrinking the core, because we can still get this savings. Maybe we give up a little bit of energy savings, but we gain a lot in the lifetime. And we're also having the opportunity, if it is a bottleneck, to remove that bottleneck. And that's another area where these savings really start to go through the roof. It is mindful, SMCs have higher magnetic losses, so it is important to appropriately design the impeder core and the cooling circuit. That's why we're focusing with the partners and who understand this and designing impeders together with them and making sure we check all the boxes, and then of course testing it so we don't waste your production time. And then just acknowledgement, there's been quite a few people working on this project with us. A lot of the analysis was done by Sean Meiskens and Saadiv Khatri. Testing and cores have been prepared and tested by Sean, Saadiv, also Joe, Doug, Todd, Chris, and Dave over at Fluxtrol. And then welding tests, they were carried out at Princeton Company. That was funded by the German Federal Ministry for Economic Affairs and Climate Protection. They're actually funding this work now because of the huge potential for carbon reductions and putting energy back on the grid. Thank you very much.